Start. Okay, so this is machine learning episode 2. I guess all of you have attended episode 1 except episode.
How do you remember that? Actually, it's true.
Right? You were on leave in Delhi.
Okay.
Wow.
He is training.
Oh, you took attendance at that time?
I basically look around, okay. But you have learned machine learning, is it?
No, I mean,
What is your
for me,
machine
machine
learning
learning is if-else condition, like bunch of if-else conditions.
No, okay. Anyway, even if you haven't learned machine learning, we'll get a quick overview of what we have talked about last time. So just do a quick review. So first question, Mukesh, can you tell me what's machine learning?
So I can.
Oh my God, we are going to have questions. Thank God I was on leave. Now I'm happy I was on leave.
I didn't revise my notes, so I cannot.
Okay, so machine learning is about finding a function. Keyword is function, is to find the function mapping to serve your purpose. So we have some examples with this last time. So for example, speech recognition, object detection, and face recognition, they're all machine learning tasks and they're all just function mappings. So for, laser point. So laser point. Mouse. And yes, okay. Yeah, so for speech recognition, the input of function is just a special grammar of speech and out a sequence of words. That's your translation of your speech. Yes. Hey, can I ask you what's machine learning?
What's machine learning?
Yes.
Something cool. Something is hype now.
Okay, anyway.
Something that can help you increase your salary.
Yeah.
Yeah.
Is it? Yeah, something hype and cool and help you increase salary.
Okay.
Correct?
Maybe.
Yeah, if you do trial and error, that's hacky, but if you do fast enough, that's machine learning and pays 4 times your salary. Cool.
Or is it a synonym to if else? Is it a synonym to
That
No,
if
it's
definition
not
I gave.
else. If you're talking about it, that's
That's the definition which I gave. Bunch of if-else.
Hey, but that is, oh yeah, bong is false. Okay.
Bong is false. Oh yeah.
Yeah, so face recognition, the input to the function is an image and also along with the label of the person you want to verify against. So the output is just a true or false to say whether this person matches this image. Hi. Have you learned machine learning?
Huh?
Have you learned machine learning before?
yeah.
Okay, then it's fine.
What is
Okay,
it?
Then it is fine if you said no.
What is machine learning?
You should ask him, yeah. What is
Yeah.
machine learning?
what is machine learning?
So basically, from a given data, we are trying to infer something. We
Yes,
keep that data somewhere to infer to basically reach to more meaningful outcomes in a later.
yes, yeah. So I told you about using data to learn a function, right? The function to generate some output given some input, right? Am I right?
Yeah.
Okay. So that's machine learning. So now we know machine learning is just finding a function mapping. So given a problem, a real life problem, how do you know whether it's a machine learning problem or not? There are 3 elements we need to identify to tell whether it's a machine learning problem.
Experience, task, and performance.
Sorry?
I mean, there should be a set of tasks.
Yes.
Against that, there should be a performance measure, say call it P, and there should be a value to denote the experience. So over time, if I keep doing the task, as experience improves, my performance should improve in that task.
Yes, but that's about human learning, right?
I mean,
Yeah, but you kind of hit my point. So basically for function, you need to know what's the input to a function and what's the output of a function. And you have the way to measure, as you said,
yeah, like 3
how good
mathematical
is it,
sets. Yeah.
and you want to improve the outputs of the function, right? So take Pikachu recognition task as an example. So for this task, we want to train a function that takes an image, which you know the structure is just a 3D matrix, and we want to output a binary value to tell whether it's a Pikachu or not Pikachu, right? And what's the way to measure the goodness of the output?
Human eyes.
Yeah, predefined data sets.
Yeah, you use your predefined data sets and to evaluate the accuracy of your output of function. That's how you measure the goodness of the outputs. Okay. So now you know the input structure and output structure and measure how do you find the function that can optimize the outputs? Satyan, do you have any idea?
How do we?
Find the function.
Find the function that can optimize the outputs.
So basically, there are different models for different type of.
Yes, so different structures, different structured functions. And
Like supervised classification is there. There are different methods.
Yes.
And supervised.
yes, that means when you train the function to tune the parameters to give you the output, right? So in order to find the function, you find out the structure of the function and then derive parameters to optimize the output. So talking about function structure, we have linear function structure, polynomial function structure, and this one called neural network, which is just actually a representation of a very complex function structure, right? So which function structure will we pick? In this case, we are taking an image as input and want to do verification on the image. Which one do you think is good? The third one. Why?
It's complex.
Yeah. Congratulations. Okay. Because it's complex, so it can represent more functions. So it's more likely to be able to represent the function we want to find. That's why we pick neural network in this case. So after you pick the structure and you find out the parameters to optimize the outputs, right? So in order to do that, you need to find a predefined data set. So for our case, we want to find out images of Pikachu and images which are not Pikachu. And we label it by humans. So that humans to give the ground truth. So the data set might look like Pikachu with label 0, with image not Pikachu label S1, right? And then we want to find out parameters that can minimize the difference between the true label and their function outputs. So this is a function's prediction. This is the true label. With the square difference, it's just kind of measure of the mistake your function made, right? We want to minimize that mistake. So how do you minimize that?
Linear
Gradient descent.
Yes, gradient descent. Okay.
What is linear regression?
Linear regression is another thing. Okay, so gradient descent.
Mathematics or physics?
So for gradient descent, it's just like plotting your loss function or the mistake function against your parameters, and you randomly pick the starting points, and they just go down the slope, and hopefully you can find out the parameter where it gives you the minimum loss.
No, a lot of effort on the presentation.
Right?
Yeah, it went like, yeah.
Yes, correct, right? But as I said, it might not always be like this. Yeah.
Yeah.
But hopefully it can reach this. Okay, that's the overview of the machine learning. Is everybody clear?
It's interesting till now.
Okay, clear. So last time we talked about AlphaGo, right?
Last time?
Yes. Okay, you're not there.
You shouldn't have said that function.
This is like half a year ago.
You get -5.
Is it half a year ago? Half a year
It
ago.
was a long
Kind
time
of half a year ago. Yeah, half a year ago. So last time we talked AlphaGo. So we'll continue from there. Today. But before let's discuss, let me just give a disclaimer. So I might not really know it because AlphaGo is not open source. Second thing, it only has one public official paper,
Yeah.
right? And that only gives you a high-level overview of AlphaGo. So there are lots of details they don't cover, so I have to tell you based on my understanding. Okay. So what's the input structure of AlphaGo? You want an AI to play the game of Go, what should be the input structure?
The bot.
The board. The board, right?
position of all
The positions of all your stones, and yeah. And what's the output structure?
Next move.
The next move, right? So what's this, in terms of mathematical terms, what's the structure?
Matrix.
Coordinate.
Coordinate, yes, you say coordinate is a matrix, right? Okay, so let me tell you, basically they use matrix rather than coordinate because coordinate has to be discrete number. But it's very difficult to train a function that outputs discrete number. Basically, that's due to mathematical reason. So it might output something like this, where each value in the cell is like a score for that move. So in this case, it gives higher score for this move. So this function thinks this move is the best. and second best move are this and this. Accept that?
Okay.
Okay. So from there, we can just sample a move. Do you know what I mean by sample a move?
Can you explain how Go works?
How
Is
Go
there
works?
only one thing you can move?
The game.
You can
Or
put a
could you move,
stone
like, 10
anywhere.
different.
You
If
can
there's
put-
only one stone.
Sorry,
Is there only one stone?
at one cell.
Oh, so the game is every time you put a stone to a cell, and somehow you win.
Oh, you don't move them around.
You don't
Yeah,
need,
yeah,
you
you
just
just
add
put
up.
a stone.
I think you have to create a path or something.
When you cross.
No,
then
if you surround your opponent's stones with your stone, you eat it.
yeah,
Okay.
then their stone becomes yours. So you change color and you put black and
Okay.
So you keep
So in the end, you have to turn the board into same color.
your color. Yeah, your color, not the
Okay.
same color. You
Same
lose it.
color.
Yeah. At the end is whoever occupies more wins.
Okay.
Okay. So do you know what I mean by sample move? I don't know.
sample move.
Sample move. Based on this matrix sample move. Do you know what I mean?
I mean,
you
it has,
use that move and put it in the function.
it has 3 possible moves. So it's
Three possible moves.
the height.
So the way you sample move from here is just generate a random number between 0 and 1. So if it's below 0.8, you take this move. If it's between 0.8 and 0.9, you take this. If it's above 0.9, you take this.
Okay.
You generate a random number.
Okay, why don't pick the higher score then?
Okay,
Yeah.
that's another question we'll talk about later. Okay, but for now, just take it as it is. We'll sample move from here.
Okay.
So how to measure the goodness of the output?
You have a higher chance of winning.
Sorry?
You have a higher chance of winning.
I mean, if
Yes, that
you
has
counter
higher-
a piece in the next move, it was a good move.
You need to play.
But
But
yeah,
yeah,
we
you
need to
play, like,
whole game
every-
and
Yeah, I'm also not very sure how it works.
You
But
don't really need to
Very
know
long.
anything about the game of Go. You can also come up with something that can measure the goodness of the output.
For example, if you were brute forcing, you were traversing all the paths that we can go through. So then 80% of paths are winning paths for us in that cell.
Yeah, it's kind of like that. Yeah, I think you're getting the point. So
But-
basically, if the function has higher chance to win, then it has, we consider it as a better function, right?
So higher chance to win means they have to play the rest of the game, every possible move.
Yes. Okay, so let's say we are training a function, start with random function, and want to play with someone. Then we can measure the chance of winning of that function, right? So let's say we are using F to play with someone. We'll let F play with Vaughn.
yeah, definitely winning.
Okay,
Vaughn-
well,
Vaughn
let
is
F
winning.
play with Vaughn. And we let's say let F play with Vaughn for n rounds, and of n rounds, we count how many rounds it wins. That's the kind of the measure for winning rate for that function.
If it plays with me, then every square is 1.
Hmm?
If it plays with me, every square is the same chance of winning.
What do you mean by every square the same chance?
Because it doesn't know how to play.
Yeah,
That is 100%.
because we start F as a random function, it also doesn't know how to play. Okay. So we'll record the each game we play. We'll start with-
how will you create this F function? Which I mean, I didn't get the idea. Like you said that you'll create a random function and you don't know how good it will perform. Like,
Yeah, we start with random
You'll
function.
start with
Then
random
we start
moves.
playing with Vaughn. Then we just try to tune the function to increase the chance of winning. Okay. It starts as with random parameters. Okay.
okay.
Okay. So we start with game, and it starts with the empty board. We call it 0. So we pass it into our function f. It will output action. We call it a0. Pass it to Vaughn. Vaughn will take a move. I give this s1. Pass it to f again. We got a1 all the way to the end. Let's say we lose the game. Okay. And we play round 2 and record in the same way. Round 3 we record in the same way. Okay. So if you look at these 3 rounds, the chance of winning is 1/3, right? So now is the time we want to tune the function to increase the chance of winning, right? So basically, you want to increase the scenario, the likelihood of this kind of scenario. Okay? Can you accept that? So now we'll show you how the likelihood of this scenario links to the function, how they relate to each other. Okay. Now I'm going to show you some mathematics. So be prepared, and Mukesh, get prepared.
Let me get my glasses.
Okay, so we want to calculate the likelihood of this scenario happening, right? According to our probability law, PAB is equal to PA times PB given A.
I remember. I just
Bayes
remember the
theorem.
formula. Bayes.
Conditional probability and Bayes.
Yeah, conditional probability, you remember, right? Okay. So according to that, it's equal to P S0 times PA0 to AT given S0. Correct, right, Mukesh?
Oh, yes,
What
yes,
are the
yes.
S's and
Yeah.
A's?
Yes.
I just remember.
By
the
waiting bulbs.
Ah,
I remember it.
So Mukesh has studied most math among all of us.
No, but I forgot.
okay, anyway. So look at the P0. PS0 is the starting state. It never changes. Starting state is always NP4, so we don't need to look at that one. So we only need to look at this one. Okay. So further expand this function, we'll get PA0 given S0 times this stuff. It has two conditional variable. Okay. How to expand that? There's another law or formula. Continue to expand that to get this. But if you look at this term, PS0 given A0, remember that we take A0 after S0, right? A0 comes after S0. So S0 doesn't depend on A0. So this term doesn't make sense. This term, same thing. S0 doesn't depend on whatever happens after S0.
Why do you say so that it's not depend on like
That was the order of
Because
the
that is
events,
the
right?
first
S0 was the state, like empty
initial
board,
state.
A0 was...
S0 is the state that we get after applying A0 or
S0 is the empty
it's
board.
before that.
Empty board.
Empty board. So these two terms doesn't make sense. Ignore it. So continue to expand this term. We get PS1 given A0 times this term. So Varun,
Yeah.
look at this one and this one. What do you realize?
Okay, let me see.
This one and this one.
What's the next event?
They are
Just
in the
remove A0.
same form, right? This starts from A0 given S0. This starts from A1 given S1. So if from here we can get PA0, if from this term we can get PA0 given S0 and PS1 given A1, what do you think we can get from this term?
PS2, A2, A1, sorry. No, sorry.
PA1 given S1
S1, A1, sorry.
and S2 given A1.
Yeah.
Exactly. Okay. So just keep expanding like that. You end up with this term. Okay. Product of AI given SI times product of PSI given AI minus 1. And this term, SI given AI minus 1, what does that depend on?
SI minus 1.
SI given the previous move, basically.
Yeah, SI given the previous move we take. So we take move AI minus 1, then Vaughn take a move which results into SI. So this term depends on Vaughn. Can you accept that?
Yeah.
Yes. So it depends on Vaughn, but it doesn't depend on our function, right? So we don't need to look at this term. Can you accept that? Okay. So the probability, okay. Sorry, I need to re-explain everything.
Jason sees a new candidate to ask questions. Yeah.
Last question.
Okay, so this whole probability boils down into this. Okay. So how does this relate to F? Just now we said F take a state and output a matrix, right? And we sample move. So let's say in this round of game, we took this move, which is the second row and third column, this one. So where's PAI given SI? .8, right? Yes.
Which one? Never mind.
Okay. So how to transform this into this P? P is a scalar value. This is a matrix, right? So simple mathematical transformation, multiply with the row, one hot row vector, and multiply with the one hot column vector. We get 0.8. Okay. So PAI given SI can be written as this form: a row vector times FSI times a column vector.
It's a transpose of the column vector.
Yeah, so a transpose of row vector, this is column vector. Accept.
But you said we pick any of those three.
Yeah, but in this particular round of game, you actually take this one. Okay? And here the AI are all the actions you actually took. Right? The AIs are the actions we recorded during the game.
So with this formula, we're only doing the highest, or most
No, might not. If you took this one, then I will be taking this one. Sorry? It depends on which action you actually took during the game.
But then if he didn't take the actions, then the cell will have 0%, right?
Which one?
I mean, if
No,
the cell got 0.1, that
Yes.
means that the function just output 0.1 doesn't mean that he take that move.
Yes, doesn't mean. For example, move from there. It's most likely to take this move, but it might also take other moves. Okay, too confusing, but anyway,
Always 2,3 pointed, should be 0, right? That is 3,
no, this is the third colon. I mean, this is the second row and third colon. Yeah, I mean the position. Okay. Anyway, if you don't understand this, okay, just know the scenario of this, the probability of the scenario is directly or positively related to your effort.
Did I press anything? No, it's not.
I think it's good.
It's fine.
Oh, it's better than
Yes, but
Okay, so that's for one. Okay. So that's for one round. The one we calculate is for one scenario, right? For one round of game. So for n rounds of game, we can use variable r to record the result. We record 1 if we win, -1 if we lose. So how do you optimize the chance winning? We want to increase this scenario. Still remember what's this? The probability of the winning scenario, okay? And when r is equal to -1, which means we lose in that round, we want to minimize the probability of this scenario. Okay, accept? Okay, if further expand, you get this. Okay, that's I would call the objective function we can optimize to increase the chance winning. Everything accept? Okay?
Yeah.
Okay. Okay. That's the end of the most difficult math we'll see today. Okay, so this is Hans' question. Why don't we just why don't we just take the highest scored move, right? Just now we say sample move. Why not take the highest scored one? So the reason is simple. During the training phase, the score given by the app might not be accurate, right? We start with a random function, so these scores can be random. So take the highest move doesn't mean it's the best move. Second thing, it's a very general topic in reinforcement learning. During training phase, you try to explore as many moves as possible. Okay, try to explore all the possibilities, all the moves, as you say, all the branches you can take, and see which branch gives you the best results. Here is a little bit digression to explain why exploration is important. Let's say today is Hans' first day in Singapore. Yes, and then he wants to pick something to eat. Before he came to Singapore, he thought laksa is the best. Second, chicken rice. Third is bihun. Okay. If we always pick the highest scored move,
Yes.
he will choose laksa.
Yes.
Right? And let's say it does taste good. It gives you positive reward. Okay. You, according to the algorithm, will increase the chance of taking that action. Right? According to the equation saw just now, so increase the chance of taking the action. So next time you'll still pick laksa. And if it still tastes good, you keep increasing the probability of that action, right? And you might end up eating laksa every day.
Until it's not taste good anymore.
Yeah.
Then it's become 0, the other two become
No.
50%.
Even if you don't feel it doesn't taste good, you will slowly decrease the chance of this, right? Slowly decrease the score for this one until the other one overtakes it, right? It might take very long until you can realize, oh, actually chicken rice is the best choice, right?
I can agree.
Yeah, actually, and if you have heard about the Gary Kasparov versus the IBM chess machine that they made in around 2000, which was the brute force version, but it was a chess engine. So it was unable to decide. In a move, it got stuck and it was unable to decide. It was unable to sample a move. and decided to just randomly take a move, and Gary Kasparov thought that, oh, it's some new move that the machine has thought, and he eventually lost because of that move, just a random move. So yeah, sampling important.
Oh,
Yeah.
I didn't know.
Yeah, so yeah, he was the grandmaster at that time for chess. So the chess grandmaster lost because a machine decided to take a random move.
Okay. So what do you mean?
The random move should be 0.0. The random move is still more than 0%.
Yeah, when you can't, yeah, when you don't go with the highest, like most likely move, and you decide to, okay,
And you still,
yeah. Never mind, sorry.
Okay, so that's just a bit digression. You can find more topics on that in reinforcement learning. So just now we said we choose Vaughn as the opponent. Yes, let's say Vaughn is very good at playing Go. If you choose Vaughn as opponent, won't our F always lose? Because we start F with a random function, right? So the chance of winning a smart guy is really, really low. Right? So typically, we'll not choose expert to play. Okay. First, it's expensive to play with expert. Second thing, you will get negative reward all the time, right? So we start training another function to play with F. What does that mean? Okay.
It's too much.
Another machine.
Okay, another machine.
So in AlphaGo, you can read the paper. They use F to play with the previous version of F. So here's the illustration. Let's say we start with the random function F0, and we train up. Well, no, don't need to train. Just get another function, a random function, which is less complex. Okay. And we train F to beat G. Just using our update function, play n rounds and update F until we can totally beat G. Okay. And after that update, you got a new function called F1. That's version 1 of F. Then you make a copy of this F1, you fix it, and we train the F1 to play with F1. So that this F1 can be this F1. Okay, this is kind of confusing, but can you get it?
You become a better self every day.
Just for example, Abhishek wants to play MMA. How can he improve himself? So first, he make a copy of himself. Okay? Then he tries to beat the copy of himself. So once he managed to beat the copy of himself, he is on new level.
Yes.
provided the copy himself never improved.
No,
His copy might be better than him.
Yeah, I said I fixed this copy. Okay, we don't improve this copy. We won't improve this one, right?
The moment you beat him, then you make yourself a copy.
Yes, then make yourself a copy again. Yes. Then you try to beat your copy yourself again. Okay. Does that make sense? Okay. Actually, a caveat here is in AlphaGo, actually, it not only plays with a previous version, it might let us play with a much older version of yourself. Okay? And this is still kind of makes sense. Let's say Han can, how should I say? Han can beat Mukesh in terms of table tennis. Mukesh can beat Abhishek in terms of table tennis. But that doesn't really mean Han can beat Abhishek in table tennis. Does that make sense?
Actually, no. You can.
It's-
But then sport always got some randomness, right?
Yeah.
But then mathematics, right? 4 greater than 2, 2 greater than 1, means 4 greater than 1.
No, it doesn't really mean. For example, Mukesh is very good at catching Abhishek's, how to say? Mukesh is very good at preventing Abhishek's attack. You are very familiar with Mukesh, but you are not very familiar with Abhishek.
It's not a mathematical function.
That's not a
No, but then all the example have some error there, right?
Yes.
So this one have some error percentage, like the wind blow the board or something.
Error percentage, what do you mean? There's no error percentage there.
Yeah. So if there's no error, yeah. So because of table tennis, there's error percentage, right? So in all the shot, there's might be an error, right? But if there's no error, it should be I'm taller than you, you're taller than someone else, so I'm taller than the other guy, right?
Yeah, but there should be error, right?
Or it should be error.
Yes, maybe different and or you also have different strategy. So your strategy might work with him, but might not work with the others. That's kind of the idea. Okay, so that's the second thing. Third thing, is it easy to train? What do you think? Okay, let me just tell you. Generally speaking, that method I told you just now is not very easy to get good results. Simple reason, Go is a very long game, right? If you ask a person to play several hours, right? There are many moves you need to make. And notice that during the training process, we only tell you whether you win or lose. Other than that, we didn't tell you anything, right? Do you think it's easy for you to learn if we only tell you whether you win or lose at the end? It's kind of hard, right? For human, it's also hard. Actually, for machine, it's also hard. And also, notice this update function. When R is positive, if you win the game, we'll try to increase the probability of all the actions you took during the game. Right? Which doesn't really make much sense, because if you win the game, doesn't mean all the moves you take are good. Maybe some good, some bad, right? So it would be better if we can give some immediate feedback when we play the game. Yeah, it'll help you learn faster. Do you agree? Yes. So that's what they come up with next. They want to measure the goodness of every single move by measuring the probability of winning after taking that move. And the approach they took is really, really simple. Okay? Okay, so we want to find a function that takes a state in action and outputs a measure of the winning rate if you take this action after that state. Okay? So how to obtain that QSA? So remember, we play n rounds with Zhang, or play n rounds with ourselves. From that n rounds, we can record lots of state action pairs, right? And also the results from that. So you can actually train a function Q to take in S and A and try to make it output the correct estimate of the winning rates. Okay. Okay.
So that is R bar.
R bar, why? Okay, R is the result of the winning rate. For example, during the n rounds, we took this action at this state many, many times, and sometimes you win, sometimes you fail. We just take the average. Okay. But do you think this is useful? How accurate can our estimate be? Right? And how accurate can our function be really depends on how much data you can have during the play. Okay? So for the game of Go, the number of states we have is really, really large. So we have 19 times 19 cells, and each cell can have 3 states, occupied by you, by your opponents, or empty, right? 3 states. So number of states is 3 to the power of 19 times 19, which is 1.7 times 10 to the power 172. And state action pairs is even more. And how many pairs can we explore in one round? Roughly the size of the board divided by 2. It's like you occupy the half, he occupied the other half. Make sense? Okay. So how many rounds do we need to play in order to explore all the pairs? It's this number divided by this number, right? That's this much. And if we assume playing one round takes 1 millisecond, that will take 10 to the power 162 years to finish. So that's literally intractable. So generally, we cannot expect the Q function to be very accurate, right? Make sense?
Yes.
Okay, since it's not accurate, so what can we do?
Then give up.
Okay. Okay, so Mukesh, let me ask you a question.
Please.
When you play what do you play, Ben? Do you play chess or?
No, I don't.
We play poker.
I don't.
He plays poker.
Oh, you play poker. Okay. How do you decide what action to take?
Depending on current situation.
You first have some kind of intuition, right? What's judging from the situation? You have some kind of intuition what you do, right?
Whether the intention regarding it depends on the current situation. Right?
Depends on how high.
Yeah, but okay. You can have lots of actions.
But yeah, in case of gambling, you can say, yeah, I have intention in doing that.
No, not really gamble.
I think what
No, you said poker.
Okay.
I think he's trying to. Is it like depth control on we don't take all possible combinations. We go into some combinations like 3 or 4 moves ahead in the game.
Yes.
And then like after 3 or 4 moves, we have a different state to start because our either we have done well or either we have fared bad, and then from there, so we'd have 2 nets basically. Never mind. Go ahead. Sorry.
Okay. I can kind of get you. So the P and Q we trained just now can kind of get us some intuition. So in the game of Go, every time, so let's say in the start of the game, how many possible moves can you make? 19 times 19. There's so many moves, right? But given your intuition, you can pick some promising moves that you feel is good, right? Then from there, we can think ahead a few steps to see how to further measure how good the move is. Agree? Yes. So that's how we're gonna do it now. We start from the game. So now which move we'll take? We first need to use your intuition, okay? The intuition we built just now is the P and Q, right? So we can pick an action that can maximize the linear combination of P and Q value. Make sense? Make sense?
Intuition can be random as well, or why did you take the linear?
Why would you take the linear? Okay, this is kind of reasonable, right? So what's the value range for P? The range for P.
0 to 1 or 0.
What about Q?
From 0 to 1.
Yeah, so both 0 to 1.
And alpha beta?
It's something you can take. You can pick.
Okay.
Yes.
Okay.
Yeah. But anyway, linear combination makes sense, right?
Means you can give the reasoning, but why linear? Why didn't we choose any other?
What do you think is better choice?
I'm not talking about the better choices. I'm just saying that.
Okay, I'm saying, okay, Tiny linear has a reason because it's fast to calculate. Okay, even you don't think about anything, it is fast to calculate. This is already an advantage.
Okay.
So based on that, we can pick an action. Let's say this one. Then we want to think ahead a few steps, right? So simulate the game to the end. Okay. But how to simulate your opponent? You need some way to simulate your opponent, right? So, okay, this is not important, but let me just tell you. In AlphaGo's case, they use something called fast draw policy. And how to get the fast draw policy? They simply collect lots of game records played by the human experts. So literally lots of state and action pairs. And they trained another function, pi, so that I can take in a state and output some move that's very close to a human expert's move. Okay, anyway, not important. So at the end, you can get a result, whether win or lose, right? And similarly, you can do more simulations to make your estimate more accurate. So from here, you can see you simulate 3 times and win twice. Okay. Then what we do is just to update our measure function, Q. Can you understand this part? This is a linear combination of the old value and the simulation result.
The Q values for that particular node.
Yeah, for that particular node. Right. Are you following me? So I want to update faster, do you think I should set lambda to bigger or smaller?
Update fast.
Well, I want to update Q faster.
Set it bigger. Set it smaller.
Yeah, why set smaller?
Because then it will be closer to the win.
Closer to this value, right? Yeah. So lambda is basically a control for you to control the speed of update, how fast you want to update the Q value. Okay. So yeah, after you update the Q value, you continue to pick using this function. You might pick another node. Okay. Maybe too much information. Let me just skip this part. Already too much information. So basically, just simulates all the way to the end, and you get another value for that. Okay. And further pick, if we pick the same node, we just expand that node You can use kind of mini-max strategy to estimate which move your opponent will take. For example, this move. And you use the same simulation strategy on the expanded node and update your winning rate estimates. Okay? Make sense? Make sense? Okay. Then just keep doing that for as much as you can within the time limits. And at the end, you pick the move that was visited the most. You know why?
More level?
No, because we pick which node to visit based on this value, right? So if you pick some nodes very often, that means it gives you very high value for P and Q consistently, right? If some node gives you very high value of P and Q, it will always give a high value for this linear combination. It will pick this very often. Does that make sense?
Pick the most visited node, or you should pick the
highest
which has the highest
node.
Q value?
Yes, I'm also seeing that question, but their official answer is pick the most visited node. But I think pick the highest scored
If
node.
I am dumb and I keep visiting the same last node, I guess.
Then there is a particular set of moves that you will always win against a dumb player. So in that case, Q would be higher and frequency would be low.
Yeah. Okay. I think kind of both make sense. You can pick the highest scored move or the most visited move. Okay, that's it. Let's just do a quick summarization. How can you become a good Go player? There are two parts. First, you need to get very good intuition. Second thing, based on intuition, you just think ahead a few steps to make your intuition more accurate, right? So how to gain good intuition? Start with some random intuition first. Then we play hard. Play lots of games and record each of the game. And from the records, try to increase your chance of winning using this update function. Okay? But this F is not very easy to train and also very time consuming to train because you need to play lots of games in order to do some updates on F. So we train another kind of intuition function called Q and we combine them together. And how to look ahead? Based on intuition, pick some notes, pick some promising moves, and look at them. And look ahead from those moves and do some simulation. Then update your intuition according to simulation results. And go back, loop around. Okay, that's the basic strategy taken by AlphaGo. Some key takeaways. How can you become a Go player? You need to play a lot first. You need to try to overcome yourself, right? Try to beat the previous version or older version of yourself. And it's better to get some quick feedback when you play the game rather than only getting a feedback at the end. You should explore more options that don't look promising to you. Next time, try some food that you thought is not good. It might give you a surprise. And besides intuition, you also need to look ahead and do some simulation to make better decision, right? Okay, so that's the end. Do you have any question?
So did they ever train by playing against humans eventually?
No.
No.
You don't want to train that to play against humans. Humans are expensive.
I mean, after beating all the previous versions.
Yes.
So literally, it can beat once it can beat its like best version of itself. It can beat a human.
Now it's ranking run number one.
They set up a bot on the
Online.
online
they have
to play
online
versus
bots.
a real player. Like trying to be like a real player.
Also, I'm assuming that they learn from the games they have played during the competition also. So like once Lee all actually defeated, like in three games, one game he defeated them. So I'm assuming they learn from that also.
The past games, whether the computer was involved or not, they can learn from
The past games, yeah, actually just now mentioned, they actually use the past game to change the what called
Fast
pastoral
forward
policy.
policy.
Yes.
Okay. Yeah.
Zhang is talking about really playing with human, right? Yeah, they do that, but doesn't rely on that. They rely on train another function to play with the function.
So you said intuition and you said exploring things, right? Those are quite opposite, right? Like if I use my intuition, I won't explore because I always would go for.
Yeah, that's actually a trade-off. You need to trade off between these two. There's actually a discussion in machine learning. It's called exploitation versus exploration. This is always a trade-off you have to make. Yeah. So there's no perfect answer for that. Do you get it? Understand? Really?
Except maths.
Sorry?
Except mathematics, I understand.
Okay, anyway, if you get the overall idea, that's good.
Thank you.
Okay, thank you.